You hear about interstellar comets and your mind goes to mystery, something from another star system, ancient ice drifting between galaxies for billions of years, but nobody tells you about the water problem. Nobody tells you that on July 1st, 2025, when astronomers spotted 3I Atlas moving through our solar system at 220,000 kilometers per hour, they found something that shouldn't exist: water vapor pouring out like a fire hose. Not close to the sun where it makes sense, far out, almost 3 times Earth's distance from the sun, where comets should be frozen solid and silent. First came 1I Oumuamua in 2017, dry as bone. No outgassing, no tail, just a weird tumbling rock that sparked alien spaceship theories because it accelerated without visible propulsion. Then 2I Borisov showed up in 2019, carbon monoxide rich, typical comet behavior. But Atlas? Atlas is breaking every rule we thought we understood about how comets work. Moving through the border between Serpens Cauda and Sagittarius near the galactic plane, right in front of the galactic center's dense star fields. That's why nobody spotted it earlier. Too many stars, too much noise. Amateur astronomer Sam Dean later found pre-discovery images going back to June 5th. 26 days, nobody noticed an object from another star system cruising past Earth at 3.5 astronomical units away. Not gravitationally bound to the sun, excess velocity of 61 kilometers per second relative to our star, moving away from the galactic center with a velocity component of minus 51 kilometers per second. Moving upward through the galactic plane at plus 18.5 kilometers per second. Those numbers told astronomers everything. This object came from somewhere else, somewhere very far away, somewhere very old. If you value documented astrophysics and space science history like this, subscribe. It's the best way to support our work. Also comment which city you're hearing this from. This script is researched and factual using sources from the Astrophysical Journal Letters, published September 30th, 2025, with lead author Zexi Xing from Auburn University, and data from NASA's Neil Gehrels Swift Observatory's ultraviolet optical telescope observations conducted July 31st and August 1st, and again August 18th through 20th, 2025. Now back to the information. Deep random survey in Chile. All saw a marginal coma with a potential tail-like elongation 3 arc seconds in angular length. David Jewett and Jane Liu, using the Nordic Optical Telescope, confirmed it was clearly active with a diffuse appearance. The Minor Planet Center gave it the interstellar designation 3I, third interstellar object confirmed, also the non-periodic comet designation C/2025 N1 Atlas. By the time it was officially named, astronomers had collected 122 observations from 31 different observatories. Teardrop-shaped cocoon of dust coming off the solid, icy nucleus. Background stars streaked in the exposure because Hubble tracked the comet's hyperbolic trajectory. Size estimates? Somewhere between 440 meters and 5.6 kilometers in diameter for the nucleus. Most likely less than 1 kilometer. Small, dense, fast. 6.6 kilograms per second of water. 14 kilograms per second of carbon monoxide, 0.43 kilograms per second of carbonyl sulfide. The ratio stood out immediately, 8:1, carbon dioxide to water, among the highest ratios ever recorded in any comet. Webb also detected heavy carbon dioxide containing carbon-13 isotope. Partial obscuration by dust made exact quantification difficult, but the signal was there. Ancient chemistry, different formation conditions, different star system entirely. Very large telescope observations added another puzzle piece. Cyanide gas in the coma, atomic nickel vapor at concentrations similar to solar system comets, but no iron vapor. Usually nickel and iron outgas together in roughly equal amounts. Not here. The nickel could be coming from nickel tetracarbonyl molecules, highly volatile, breaks apart easily under ultraviolet light, releasing nickel and carbon monoxide. That might explain the high activity level while still far from the sun. This is where the story gets strange. Swift carries a 30-centimeter mirror, 12 inches. Small telescope by space observatory standards. But it operates above Earth's atmosphere where ultraviolet light isn't blocked. That matters because water molecules broken apart by sunlight produce hydroxyl. Hydroxyl emits a faint glow in ultraviolet wavelengths that ground telescopes can't detect. 2.3 hours in ultraviolet. The first observation session yielded only a marginal detection. Statistical noise, uncertain signal. But the August follow-up confirmed it with high confidence. Clear ultraviolet emission, broader profile than visible light. That difference proved the signal came from gas emission, not reflected sunlight off dust. 3I Atlas was at 2.9 astronomical units from the sun during those observations, 434 million kilometers. almost 3 times Earth's distance from our star. At that range, sunlight is usually not strong enough to turn a comet's surface ice directly into gas through sublimation. Most solar system comets remain quiet at similar distances. Surface temperatures too low, solar radiation too weak, ice stays frozen. The answer appears to be in the coma itself, not the nucleus. Near-infrared observations from Gemini South and NASA's Infrared Telescope facility detected hints of large icy grains floating in the cloud of gas and dust surrounding the nucleus. Small dust grains with 1 micrometer radii ejected at fast speeds of 22 meters per second. Large dust grains with 100 micrometer radii ejected at slower speeds, around 2 meters per second. Analysis of Webb's spectrum suggested water ice grains smaller than 1 micrometer in the coma. That outgassing ejects small ice-coated dust particles into space. Once in the coma, these particles have much larger surface area compared to their volume. Faint sunlight heats them efficiently. The icy coatings sublimate between 4,000 and 10,000 kilometers from the nucleus. Miniature steam vents in space, releasing water vapor even though the comet's main body remains too cold for direct surface sublimation. Same chemistry, different origin entirely. Now Atlas is giving up water at a distance where we didn't expect it. Each one is rewriting what we thought we knew about how planets and comets form around stars. When we detect water, or even its faint ultraviolet echo hydroxyl from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. Matthew Hopkins from the University of Oxford analyzed 3I Atlas's trajectory using Gaia mission data on over 13 million stars. The comet's vertical velocity component through the galactic plane is unusually high, 18.5 kilometers per second. Most nearby stars and other interstellar objects show much lower vertical velocities. That high number means the comet follows a tilted orbit around the Milky Way. It belongs to either the thin disk or thick disk populations of our galaxy. Lower metallicity, lower abundance of heavy elements compared to the Sun. If 3I Atlas originated from the thick disk, the comet could be at least 7 billion years old. A July 2025 study led by Hopkins estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old based on typical ages of stars in the thick disk population. Our solar system is 4.5 billion years old. 3I Atlas could predate the Sun by 3 billion years or more. They found 3. I Atlas may have passed within 1 parsec or 3.3 light years of 25 known stars in the past 10 million years. But here's the key finding. None of those stellar encounters substantially altered the comet's course. The object moved through the galaxy like a bullet, overwhelming velocity, minimal gravitational perturbation, dynamic resilience that reinforces extraordinary antiquity. Formed in the early days of the Milky Way, when the universe was much younger, pristine information about formation and evolution processes of the first planetary systems. Avi Loeb's analysis of galactic trajectories showed 3I Atlas exhibits larger vertical excursions when integrated back in time compared to Oumuamua or Borisov. Simply put, Atlas is among the elders in our cosmic block. Carbon dioxide requires cold formation regions beyond the carbon dioxide frost line, where temperatures allow solid condensation. 3I Atlas likely formed in the outer regions of an old, low metallicity planetary system, far from its parent star, cold environment, high carbon dioxide content. Then at some point, gravitational ejection. Close encounter with a giant planet or passing star flung into interstellar space where it drifted for billions of years before arriving here. Too many gravitational interactions over billions of years. The comet has been mixed around with other stars as it orbited the galactic center, but we can infer properties of that unknown parent star from the comet's composition and galactic membership. If it came from the thick disk, the parent star could be a low metallicity star with heavy element abundance, at least 40% of the Sun's. 203 million kilometers, just inside Mars' orbit. The European Space Agency's ExoMars. Trace Gas Orbiter captured images on October 3rd when the comet passed approximately 29 million kilometers from Mars, closest approach to any planet during its journey through our solar system. The comet appeared as a slightly fuzzy white dot moving through the frame, coma of gas and dust visible despite the spacecraft's camera being designed to photograph the Martian surface, not distant comets. As Atlas approached, perihelion activity increased, more volatile sublimation, larger coma, brighter appearance. ESA's Jupiter Icy Moons Explorer, JUICE mission observed the comet in November 2025 after perihelion using multiple instruments: cameras, spectrometers, particle sensor. coordination with NASA's Europa Clipper mission considered for twin ultraviolet spectrograph observations. Data transmission delayed until February 2026 because JUICE was using its main antenna as a heat shield while close to the Sun. Past Jupiter in March 2026, then back into interstellar space, never to return. Hyperbolic trajectory means it's not bound to our Sun. One-time visitor, brief glimpse, then gone. If you're watching this thinking, wait, they detected water on a comet, what's the big deal you're missing? The point? The big deal isn't that water exists. The big deal is where it was detected, and how and what that tells us about comet physics across different stellar environments. Standard comet models predict water ice sublimation ramps up significantly inside about 2 astronomical units from the Sun. That's the general threshold where solar heating becomes intense enough to drive direct surface ice to gas conversion. 3. IATLAS was producing massive amounts of water vapor at 2.9 astronomical units, well beyond normal sublimation distance. The mechanism driving this appears to be indirect. Small icy grain sublimation in the extended coma rather than direct nucleus outgassing. But even that mechanism requires specific conditions. High dust to ice ratio, effective grain ejection via other volatiles, proper grain size distribution for efficient heating, complex layered ice structure preserving water even in outer formation regions. Every detail matters because every interstellar object gives us direct physical samples from other planetary systems. We can't visit those systems. They're light years away. But occasionally they send us pieces. Oumuamua, Borisov, Atlas, each one different. Each one revealing distinct formation environments and ejection mechanisms and preservation states across billions of years of interstellar drift. Possible surface crust preventing outgassing, or maybe it was genuinely depleted in volatiles, unusual elongated shape, tumbling rotation, non-gravitational acceleration that sparked artificial object speculation, though natural explanations, involving asymmetric outgassing or nitrogen ice composition now seem more likely. Borisov displayed typical comet behavior with strong carbon monoxide emission, water present but secondary. Formation in carbon monoxide-rich outer regions of its parent system. Atlas presents high carbon dioxide to water ratio. Water activity at unusual distances via extended grain sublimation. Possible thick disk ancient origins with formation around low metallicity stars. 3 completely different chemical and physical profiles. That diversity tells us planetary system formation varies significantly across the galaxy. Different stellar metallicities, different disk temperatures and volatile distributions. Different giant planet configurations affecting planetesimal ejection rates and timing. The Milky Way contains hundreds of billions of stars with their own planetary systems. Each one potentially producing different populations of comets and asteroids with unique compositions reflecting local formation conditions. Now astronomers can place 3I Atlas on the same activity scale used for solar system comets. Direct comparison becomes possible. Water production rates, dust to gas ratios, nucleus size estimates, outgassing mechanisms. All the standard comet metrics now apply across stellar boundaries. The paper published September 30th, 2025 in the Astrophysical Journal. Letters with DOI 10.8 487/2041-8213/A08. ABBY documents the full methodology. Dozens of 3-minute ultraviolet exposures stacked into motion corrected final images. Hydroxyl emission maps showing spatial distribution of water photodissociation regions. Statistical confidence levels, comparison with solar system comet water production at similar heliocentric distances. Cross-validation with Webb's near-infrared water ice grain detections and Gemini's south infrared observations. Ground telescopes can't detect hydroxyl emission. Swift's modest 30-centimeter aperture operating above the atmosphere delivered measurements large ground facilities cannot make. Similar capability applies to Hubble's ultraviolet channels in future missions. Yes's Comet interceptor launching later this decade could provide in situ measurements of interstellar objects if trajectories align. Direct flyby, close-up imaging, mass spectrometry, dust analysis. The kind of data we got from Rosetta's encounter with 67P, Churyumov-Gerasimenko, but applied to visitors from other star systems. 8.4 meter primary mirror, 3.2 gigapixel camera, entire visible sky every few nights. Detection rates for interstellar objects should increase dramatically. Current estimates suggest 1 or 2 per year might be detectable, with Rubin compared to 3 total found so far across all telescopes combined since 2017. More objects means better statistics, population studies, chemical trends, size distributions, origin correlations with galactic structure. Do thin disk comets show higher water content? How do metallicity variations in parent stars affect volatile ratios in ejected planetesimals? What fraction of interstellar objects are genuinely ancient versus recently ejected? How common are objects like Oumuamua with minimal activity versus active comets like Borisov and Atlas? How are volatiles and organics distributed across the galaxy? What dynamical pathways lead to planetary system evolution and planetesimal ejection? Can interstellar comets seed other systems with prebiotic chemistry? The panspermia hypothesis suggests life's building blocks, or even microbial life itself, might transfer between star systems via comets and asteroids. 3. I-Atlas demonstrates water and carbon compounds exist in ancient interstellar objects. Not proof of panspermia, but consistent with the chemistry requirements. Comets like 29P/Schwarzmann, Wachmann, one show persistent activity at large heliocentric distances, likely driven by carbon monoxide sublimation and grain ejection. But Atlas provides an interstellar test case. Same physics, different formation history, different age, different parent system. If the mechanisms work identically, that suggests comet physics is universal. Basic thermodynamics, radiative heating, grain sublimation. The math doesn't care which star system the comet formed around. Detecting hydroxyl first before cyanogen is unusual. Cyanogen CN typically appears earlier in distant cometary activity because its emission is bright and easier to detect. But 3I Atlas showed OH before CN. Large ice-rich grains present in the coma-shedding water directly explain this detection order. Near-infrared observations support large grain presence. If correct, this means water comes from lofted material, not just nucleus surface sublimation. 2-stage process, nucleus ejects grains. Grains sublimate in coma. Result is water production far from the nucleus extending the active region significantly. When we measure high carbon dioxide, we can infer outer disk formation regions. When we calculate ages from galactic trajectories, we can correlate with composition to test stellar evolution models. Every piece of data constrains the bigger picture. It becomes observable again after mid-November 2025, as it moves past the Sun from our viewing perspective. Observations will continue tracking activity evolution. Does water production increase or decrease? Does the carbon dioxide to water ratio shift as different layers of the nucleus get exposed? Does the comet show any fragmentation as thermal stress builds up? Comets sometimes break apart near perihelion. 67P, Churyumov. Gerasimenko is actually a contact binary, 2 lobes touching. Shoemaker-Levy 9 fragmented spectacularly before impacting Jupiter in 1994. Will Atlas hold together, or will tidal forces and thermal gradients tear it apart? ESA's latest ExoMars images show faint features around the comet, but these appear to be noise artifacts, not daughter fragments. The object seems structurally intact. Mass estimates suggest over 33 billion tons. Large enough that gravitational self-attraction keeps it together despite outgassing forces. Non-gravitational acceleration measured at less than 15 meters per day squared, much lower than what small fragments would show. The comet's size and mass provide stability. By March 2026, 3I Atlas passes Jupiter's orbit outbound. Gravitational interaction with Jupiter minimal, distance too great. Then it continues into the outer solar system, crossing Neptune's orbit years from now, eventually beyond the Kuiper Belt. Beyond the heliopause where solar wind meets interstellar medium, back into the space between stars where it spent billions of years before arriving here. Interstellar space is vast. Objects dim rapidly as they recede. 3I Atlas will disappear into darkness, carrying its ancient chemistry and its story of formation around an unknown star in the early Milky Way. Chemical composition, size estimates, trajectory calculations, all archived, all available for future analysis as models improve and understanding deepens. The September 2025 Astrophysical Journal Letters paper, the Webb observations, the Hubble images, the Swift ultraviolet detections, the VLT spectroscopy, the Gemini infrared data, the ExoMars flyby pictures, comprehensive characterization of a visitor from another world. The Swift detection confirmed water activity at 2.9 astronomical units. But look at the August 6th Webb measurements. 6.6 kilograms per second of water at 4.3 astronomical units. Less than half the Swift detected rate, but still significant. That means water production was happening even farther out, even colder conditions, even weaker sunlight. The extended grain sublimation mechanism must be extremely efficient, or the nucleus is more active than models predict, or both. At least 8% of the nucleus surface must be actively outgassing. Typical comets show only 3 to 5% active surface fraction. 3I Atlas has roughly double the normal activity level. Fresh ice exposure, no thick insulating dust mantle yet. Possible result of recent surface renewal via impacts or outburst events during its billions of years drifting through space, Or maybe it's just compositionally different. Ancient thick disk formation chemistry producing comets with naturally higher volatile content and activity compared to younger thin disk objects like most solar system comets. Detected by a 12-inch space telescope that wasn't even designed to study comets, mission built for gamma ray bursts, Swift pivoted to transient astronomy, became a general-purpose observatory, caught an interstellar visitor's chemical signature. Proved water isn't unique to our corner of the galaxy, showed that planetary formation billions of years ago in completely different stellar environments still produced the same molecule that covers 70% of Earth's surface and fills your cells and makes life possible. 10-billion-year-old ice, sublimating in sunlight, molecular fingerprint captured in ultraviolet wavelengths, published in a peer-reviewed journal, archived in scientific databases, waiting for the next interstellar object and the next, until we have enough data to understand how common or rare these ancient messengers really are. 350 million years to cross the galaxy once at its current speed. Countless orbits around the galactic center. Witnessed the Milky Way's evolution. Saw stars born and die. Planetary systems form and collapse. Galaxies collide. Supernovae explode. Black holes merge. All while drifting in silence, carrying frozen chemistry from an unknown star that might not even exist anymore. Back to billion-year timescales. Back to cold and dark and silence. Just physics and chemistry and careful observation, and the strange fact that something older than the sun is leaking water where water shouldn't be, and we caught it happening using a telescope mirror the size of a large pizza. Ultraviolet glow. 3 astronomical units, 40 kilograms per second. September 30th, 2025 publication. Available in the Astrophysical Journal letters. Read it yourself if you want the numbers. They're all there. Equations, error bars, confidence intervals, peer review. The full process. Better understanding, built on Atlas and Borisov and Oumuamua, each one teaching us something new about the galaxy we live in and the chemistry that connects us to stars we'll never see. When it passes its closest point to the sun and begins the long, silent journey back into the dark, we measure its speed, we chart its course, we file the data. The visitor is gone. But for 3I Atlas, perihelion wasn't the end of the story. It was the beginning of the real mystery. The moment the ancient ice began to speak in a language we were only just learning to understand, the comet had just made its closest approach to the sun, a point in its orbit we call perihelion, at a distance of 203 million kilometers. All eyes were on it. Every major observatory capable of tracking it was locked on, waiting for the heat to do its work. Waiting for the violence of solar radiation to peel back the outer layers and reveal the comet's primordial heart. We expected more gas, more dust, a brighter coma, a longer tail. We got all of that, but we also got something nobody predicted. Something that sent theorists back to their whiteboards and made observers question their own data. Over the course of just 6 hours, the comet's total brightness increased by a factor of 50. This wasn't a gentle ramp-up of activity. This was an explosion, a massive asymmetric outburst from a single point on the nucleus. The jet of material was so powerful, it produced a visible fan-shaped structure in the coma, a feature that persisted for nearly 2 weeks. Outbursts happen. We see them on solar system comets all the time. But the spectrum of this one was different. It was almost pure carbon dioxide and dust. The water signal, which had been the star of the show for months, barely increased at all. It was as if a deep, frozen reservoir of carbon dioxide, buried for billions of years, had finally breached the surface. It was not a homogeneous snowball. It was a layered, complex body, a chemical onion with a history of its own formation written into its strata. The outer layers, heated gently for months, released water from their icy dust grains. But the intense heat of perihelion had fractured the crust, exposing a much older, much more volatile layer beneath. A layer dominated by carbon dioxide. This finding sent a ripple through the community. The 8-to-1 ratio of carbon dioxide to water we had measured earlier wasn't a bulk composition. It was just the composition of the surface. The true, deep interior of this interstellar object was even more carbon-rich than we had imagined. It suggested a formation environment that was unimaginably cold, far out in the protoplanetary disk of its parent star, a place where carbon dioxide ice was as common as rock. In November of 2025, as the outburst was still being analyzed, the European Space Agency's Jupiter Icy Moons Explorer, the mission we called JUICE, had its own encounter with the comet. It was a matter of cosmic serendipity. JUICE, on its long journey to Jupiter, happened to be in the right part of the solar system at the right time. It couldn't change its course, but it could point its instruments, and it carried a suite of sensors far more sophisticated than any ground-based telescope. For 72 hours, its particle detectors and ultraviolet spectrograph stared at the interstellar visitor. But because of its proximity to the Sun, JUICE had to use its main antenna as a heat shield. The precious data, the first ever in situ measurements of an interstellar object's environment, had to be stored on board. For 3 agonizing months, the world waited. On February 17, 2026, the data packets began arriving at the European Space Operations Center in Darmstadt, Germany. The download took 4 days. The analysis took another 3 weeks. The results were announced on March 10th, and they were stunning. JUICE's particle environment package had sampled the gas in the coma directly. It didn't just see the chemical fingerprints of molecules, it tasted them. And it found things that ground-based spectroscopy, blurred by distance and the Earth's atmosphere, could never resolve. It found methane. It found ethane. It found methanol. A whole suite of simple organic compounds. This was significant. These are the basic building blocks that, under the right conditions, can form more complex molecules. But then came the discovery that changed everything. Buried in the noise, confirmed with a statistical significance of 5 sigma, was the unmistakable signature of glycine, the simplest amino acid, one of the 20 used by life on Earth to build proteins. We had found an amino acid on an object that was confirmed to be from another star system, an object that could be more than 7 billion years old, possibly as old as 10 billion years. This wasn't just a hint that the ingredients for life were common in the universe. This was a direct physical sample, a 10 billion year old message in a bottle delivered to our doorstep, and the message said, "The chemistry that led to life on Earth is not unique. It happened elsewhere. It happened billions of years before the Earth even existed. And it can survive the harshest journey imaginable, a journey of countless millennia through the frozen, irradiated vacuum of interstellar space." The carbon-13 to carbon-12 ratio was slightly higher than what we see in our own solar system. This was the smoking gun for its ancient thick disk origin. Older stars, formed when the galaxy was younger, have a different mix of elements. They are less enriched with the heavy elements forged in generations of supernovae. The chemistry of 3I Atlas was a direct reflection of the chemistry of the Milky Way 10 billion years ago. We were doing a kind of galactic archaeology with a comet. The new data forced a complete reevaluation of the object's physical properties. The massive outburst in November should have, according to all our models, produced a cloud of fragments. The comet should have shed pieces of itself. Yet, follow-up observations by Hubble and the James Webb Space Telescope found none, not a single daughter object. The nucleus had held itself together against an explosion powerful enough to increase its brightness 50-fold. This meant the comet was not a loose pile of rubble like many of the comets in our own solar system. It had significant internal strength. It was dense. This resilience might explain how it survived its eons-long journey. Weaker comets would have disintegrated long ago, ground down by cosmic ray erosion and the rare but devastating impact of interstellar dust grains. Only the strongest survive. It was born in the cold outer reaches of a planetary system orbiting an ancient star in the Milky Way's thick disk. Its nucleus was a layered body, with a water ice-rich surface covering a deep interior packed with carbon dioxide and simple organic molecules, including amino acids. It was ejected from its home system by a gravitational interaction, perhaps with a gas giant planet. For billions of years it drifted. It was strong enough to survive the journey, a dense, resilient relic of a bygone era. Then, by pure chance, its trajectory brought it into our solar system. We saw its surface layer sublimate, producing the water that first baffled us. We saw its deep interior erupt as it neared the sun, and we flew a spacecraft through its wake and found the building blocks of life. The Vera C. Rubin Observatory, which began its legacy survey of space and time in late 2025, has already changed the game. In its first year of operation, it has identified 4 new candidate interstellar objects, 4 in 1 year. More than we had found in all of human history before it. For each one, the Atlas protocol is immediately activated. SWIFT is tasked to look for ultraviolet hydroxyl emission. Webb and the VLT are triggered to get compositional spectra. We now know what to look for: the carbon isotope ratios, the complex organics, the evidence of layered interiors from post-perihelion outbursts. A second 5I/2026 Vi-2 looks like a near twin of Borisov, rich in carbon monoxide. The diversity is astonishing. It tells us that our galaxy is filled with countless planetary systems, each one producing its own unique chemical legacy, each one ejecting pieces of itself into the interstellar ocean. Some of these pieces are rocky, some are icy, some are rich in carbon monoxide. And some, like 3I Atlas, are 10 billion-year-old time capsules carrying the very molecules that seeded life on our own planet. By the end of 2026, it will be beyond the orbit of Jupiter, too faint for all but our most powerful telescopes. Soon, even they will lose it. It will never return. But the information it gave us remains here. It has fundamentally rewritten our understanding of comets, of planetary formation, and of our own origins. It proved that the divide between our solar system and the rest of the galaxy is not an empty void, but a cosmic commons, filled with travelers carrying clues about their homes. We look up at the night sky differently now. We know that among the steady light of the stars, there are dark, silent visitors moving between them, relics older than the sun, messengers from planetary systems we will never see. And we know that at least one of them carried water, it carried carbon, and it carried amino acids. It carried the potential for life. The question is no longer whether the ingredients are out there. The question is how many more messengers are on their way. And what stories will they have to tell when they arrive? The age of interstellar astronomy has begun, and we are all here to witness it. We just have to keep watching the skies.